Visceral fat is hidden deep within the abdomen and cannot be felt or grabbed. Because it is invisible, many people doubt walking can influence deep abdominal fat stores. Skepticism grows because walking seems gentle compared with intense workouts, promising faster results today. People assume only hard training can reach fat surrounding vital organs deep internal effectively. This question persists because visceral fat behaves differently from surface fat visible externally stores. Understanding whether walking affects visceral fat requires explaining how the body chooses fuels daily. The answer depends on physiology, timing, and safety signals, rather than exercise intensity alone. The liver determines whether energy is stored or released into circulation during activity periods. Visceral fat drains directly to the liver, making it metabolically unique among fat stores. Because of this connection, the liver closely monitors visceral fat availability and usage rates. When the liver senses safety, it permits fat release for energy production during walking. If threat signals dominate, the liver favors storage over releasing visceral fat supplies internally. This control system explains why visceral fat responds to metabolic context, not exercise alone. Walking influences visceral fat indirectly by changing signals the liver receives during movement periods. The body stores visceral fat as a protective reserve rather than a harmful mistake. This fat provides rapid energy access during perceived threats, illness, or prolonged stress situations. From an evolutionary perspective, storing abdominal fat improved survival during uncertain environments historically. Fat is released only when the body senses safety and low environmental threat levels. Persistent stress signals convince the body to retain visceral fat for future protection needs. This explains why forceful exercise or restriction sometimes increases abdominal fat retention instead. Reducing perceived threat allows visceral fat to become unnecessary and therefore accessible for use. The body manages energy like a budget system with multiple accounts and priorities daily. Different fuels are withdrawn depending on activity, stress, and perceived safety signals within the body. Walking does not target fat directly, but changes the rules governing energy spending decisions. Low-threat movement encourages using slower fuels rather than protecting savings aggressively within the body. Visceral fat functions like savings released only when conditions feel predictable and safe internally overall. Walking signals stability, which gradually relaxes spending rules over time during prolonged low-stress activity. This framework explains why duration matters more than intensity for fat use during walking sessions. Stage 1: First minutes immediate fuel use. During the first minutes of walking, the body relies on circulating glucose for energy. Stored glycogen and readily available fuel supply muscles while metabolic pathways assess demand levels. At this stage, fat contribution remains minimal as the body evaluates activity continuation likelihood. Hormonal signals adjust quickly to determine whether movement will be brief or sustained activity. Heart rate and breathing begin rising to support immediate energy requirements efficiently during walking. The body waits for confirmation before unlocking slower energy sources like fat reserve stores. Stage 2: Early stabilization and fuel blending. After several minutes, breathing and heart rate begin stabilizing at a comfortable, steady rhythm. The body recognizes movement will continue and adjusts fuel strategy accordingly for efficiency. Fat oxidation begins increasing alongside glucose use earlier than most people expect during walking. Hormonal signals gradually permit greater fat contribution as perceived threat remains low and controlled. Muscles start blending fuels to preserve glucose and support sustained movement over longer durations. This stage marks the transition from immediate energy use toward more balanced metabolic efficiency. Walking is low-stress movement that signals safety rather than urgency to the nervous system. Low-threat activity allows the body to access slower fuel sources like fat efficiently. Unlike intense exercise, walking does not trigger strong stress hormone responses within the body. This hormonal environment encourages gradual fat release without activating protective storage mechanisms inside the body. The nervous system interprets walking as controllable, predictable, and safe ongoing activity for humans generally. This perception opens access to fat stores that remain locked during stressful conditions otherwise. Stage 3, 10 to 20 minutes. Fat release. After 10 to 20 minutes, hormones increasingly stimulate lipolysis, releasing fatty acids into circulation. Adrenaline and related signals rise moderately without triggering stress responses or urgency signals. Muscles begin relying more heavily on fat to sustain continued walking activity efficiently. Glucose use declines proportionally as fat delivery to muscles becomes more consistent and reliable. This shift preserves glycogen and supports longer duration movement without fatigue buildup. At this stage, fat burning becomes meaningful even though intensity remains relatively low. Insulin strongly suppresses fat release by blocking lipolysis within adipose tissue during activity periods walking. Lower insulin levels permit stored fat to exit cells and enter circulation during walking sessions. Catecholamines like adrenaline promote fat breakdown by activating hormone-sensitive lipase enzymes during walking activity. Walking elevates these hormones gently without causing stress responses that restrict fat access during exercise. The balance between insulin and catecholamines determines how much fat becomes available for muscles' energy. Proper hormonal conditions allow walking to unlock visceral fat safely over time during regular sessions. Stage 4, 20 to 40 minutes, visceral fat contribution. During 20 to 40 minutes, deeper visceral fat stores increasingly contribute energy to walking muscles. This shift requires low insulin steady duration and moderate intensity without excessive stress responses. Under these conditions, the liver permits greater release of visceral fat into circulation consistently. Muscles oxidize this fat, efficiently maintaining pace without increasing carbohydrate dependence during prolonged walking. Consistency at this stage explains why longer walks favor visceral fat reduction over time. It is duration, not exhaustion, that determines when visceral fat meaningfully contributes to energy. Excessive walking intensity increases stress hormones and shifts metabolism back toward carbohydrate dependence quickly. High intensity signals urgency, causing the body to conserve fat rather than release it. Moderate intensity maintains safety signals, allowing fat oxidation to remain active during movement. Timing also matters because fed states elevate insulin, which suppresses fat release during walking. Walking while insulin is low increases access to stored fat sources, including visceral fat. Proper intensity and timing together determine whether walking supports fat use or fat storage. Fat oxidation remains elevated after walking as muscles replenish energy and restore balance. This post-walk period continues using fat even when movement has stopped temporarily. Walking improves metabolic flexibility, allowing smoother transitions between glucose and fat fuels. Repeated walks train the body to access fat more readily during daily activities. Over time, this adaptation reduces reliance on constant carbohydrate intake for energy. These after effects explain why regular walking produces cumulative visceral fat reductions gradually. Fat burning is not an on-off switch triggered only by extreme effort or intensity. Scientific research shows low-intensity activity can maximize fat oxidation under proper conditions. The fat-burning zone concept oversimplifies complex hormonal and metabolic interactions within the body. Walking challenges myths by demonstrating effectiveness without exhaustion or discomfort. Understanding physiology replaces outdated fitness beliefs with realistic expectations for fat loss. Science supports walking as a legitimate tool for reducing visceral fat consistently over time. Walking communicates safety, predictability, and control to the nervous system during daily movement. When the body senses safety, it relaxes energy conservation rules and releases stored fat. Visceral fat decreases when it is no longer biologically necessary for protection or survival. Walking repeatedly reinforces this signal without triggering stress responses or urgency signals. This makes walking uniquely effective for reducing deep abdominal fat over time consistently. Fat loss occurs not through force, but through alignment with biological safety mechanisms.